Hi, I'm Haqq Misra, and I'm going to tell you a little bit about my energy balance model and our attempts at doing some of the TIE simulations with an energy balance model. So just as some motivation, energy balance models are one-dimensional models where the one dimension is in latitude, and historically these models were constructed to explain the biostability, the hysteresis that Earth's climate exhibits. The first EBMs were published around 1969 by Boudico and Sellers. And so you can see on the left side of the plot, on the left side of the slide, there's a schematic diagram that shows that at a particular radiative forcing, there are multiple solutions for the ice line latitude of Earth. This essentially describes when is Earth frozen, totally glacial, when is it ice-free, and when are there ice caps. And so if you start off in an ice-covered state at the bottom, you can increase or decrease radiative forcing by a small amount and nothing will change. But if you hit this transition where the dashed arrow is, then you transition from an ice-covered to an ice-free state. And the change in radiative forcing, this could be changes in the solar luminosity over time, but this could also be changes in the radiative balance from greenhouse gases, such as increasing or decreasing atmospheric carbon dioxide. You'll notice that there's various ice cap coverages that Earth can have. There's a large ice cap and a small ice cap solution where Earth or a terrestrial planet in this configuration could have a small ice cap with the latitudes around 70 or 80 degrees, and a small perturbation might cause that entire ice cap to vanish, whereas if you're at a larger ice cap, there's a little more stability. On the right side, you can see a simple EBM that I've calculated actual ice line latitudes, where the pink shows the small ice cap solution, and then the red shows the larger ice cap solution, or the pink rather shows a hothouse condition where you would drop into the ice cap solution. And so we are here. We're really near that cusp. Now you can't take this particular model to be the word of truth. These EBMs are very simplistic, and so they're instructive in telling us about how the climate system behaves over a wide parameter space of solar flux and other things that we can tune, other knobs we can turn in the EBM. But of course you have to compare EBMs with other models to get an actual sense. But in any case, we are kind of near this small ice cap solution, and that raises interesting questions for climate change. The energy balance model is described by a fairly simple equation. On the left side, we have absorbed incoming stellar radiation, where S is the stellar constant. We have 1 minus the planetary albedo, and that equals the emitted outgoing infrared radiation, the OLR, we sometimes say. And then the middle term is latitudinal energy transport. X, in this case, is latitude, so that's our one dimension that we have. T is time, lowercase t is time, uppercase t is temperature. And this D is a diffusive parameter where I won't get into that too much in this talk. That's generally a constant, although that can be adjusted based on how the planet's rotation changes. And then the final term is the thermal inertia of the ocean and atmosphere system. And so the EBM I'm using has 18 latitude bands, but it could be an arbitrary number. You can make it more, or you can make it less if you really wanted to. The thing that I'm going to focus on in the rest of this talk are these two parameters, the planetary albedo and the outgoing long-wave radiation. This is essentially how we represent radiative transfer in an energy balance model, since there is no explicit radiative transfer scheme. And so historically, the simplest thing that's been done is a linear parameterization of radiative transfer, where the outgoing long-wave radiation is just A plus B times the temperature, where A might be somewhere around 300 watts per meter squared, B might be 2 watts per meter squared per degree. And that will give you a pretty good approximation to Earth climate today. You set the albedo equal to a fixed value of 0.3. You'll get, you can configure models then to give you a mean annual temperature of 288 Kelvin. You can explore a little bit just how that temperature profile, the latitudinal temperature profile, changes with temperature. you can explore variation of these parameters A and B, but it's really impossible to represent greenhouse warming by specific species if you're interested in saying how much does the climate state warm or the latitudinal temperature distribution change if I increase CO2 from 400 ppm to 1 bar. You can't really do that in a meaningful way with this sort of linear parameterization. So another thing you could do is make a polynomial parameterization. And so this is something that we did in a 2016 paper. We were looking at limit cycles in energy balance models. And you don't have to really take this in. This is, it's obviously a kind of complicated polynomial parameterization, but this is at least attempting to make the outgoing long wave radiation and the albedo a function of properties like the surface pressure, the CO2 mixing ratio, and other variables that we might want to change, and things that you can usually change in a GCM. So this is fine. This is a little complicated. So here's a result. Now, we don't have to focus on the science here, but this is from our paper about limit cycles, where the climate changes from a glacial to a hothouse state on relatively fast timescales. But you can see there's CO2 partial pressure in soil on the x-axis. There's an outgassing rate on the y-axis. There's a lot of jagged lines in this plot. That's not making nice, smooth features like we like to see and might expect when dealing with otherwise analytic solutions at times, or solving a very simple differential equation. This is because of this ugly kind of polynomial parameterization. I mean, it's tough. And I should mention, what are we parameterizing? We are parameterizing a one-dimensional radiative convective model. This is the casting model. You run thousands of these models, and you come up with a fit for how outgoing long wave radiation changes as a function of our variables of interest, and the same with planetary albedo. So you can do that. You take this 1D radiative convective column model, run thousands of them, and you get a polynomial, but then it gives you some weird behavior. And here's just an example of like the error that you get from one of these polynomials. I admittedly picked one of the worst case scenarios just to make the point, but so for one, this is a paper that Ben Hayworth published recently, and so this is an error from the polynomial fit developed for that paper. So a median error about 8.7% in OLR, and that covers the primary range of interest for this problem. But you can see there's the error can extend out to 25%, and for some small numbers of points in this polynomial, your error can extend 35 to even up to 40% for a small number of cases. So this is fine. This is very fast to do a polynomial like this, but there is some sacrifice in terms of the accuracy you can expect. And so what I've developed, and in the current version of the EBM, is a lookup table method for radiative transfer. And so what we do is the same thing we start with for the polynomial fit. We generate a database with these one-dimensional radiative convective equilibrium models, these column models, run thousands of them to generate a database with outgoing long wave radiation and planetary albedo as a function of properties like surface pressure, CO2 mixing ratio, surface albedo, and zenith angle. If we want to add other species, we can add other species as well. And so when you then run the EBM at each latitude band, you actually look at those properties. You say, well, what's the surface pressure, mixing ratios, albedo, and zenith angle at my latitude band? And then you look up in the database, based on those values, what's the first and second nearest neighbor to the properties at my latitude band. And so you might not exactly have that in your database already, but you're pretty close, because we've already calculated thousands of these properties over our parameter space of interest. So you calculate the first and second nearest neighbor in the database. You interpolate between those nearest neighbors using a Gaussian radial basis function. And so that gives you a really good approximation of what the outgoing long wave radiation and planetary albedo are according to the 1D radiative convective model, the column model. So essentially, we've parameterized our radiative convective equilibrium radiative transfer into this database with much higher accuracy than you would get with a polynomial. Now, the flip side, the trade-off is, of course, computational cost, is that it actually is a lot slower to do this, but not prohibitively slower, and the gain in accuracy is almost indistinguishable from actually running the radiative convective equilibrium model at each time step, which would be take much longer. And so you just repeat this. You have to do this at every latitude band. You repeat this for however long you want your iteration to go. I have not yet parallelized it, but it's certainly a task that could be parallelized and speed up the computation a little bit. So we put this in the model. This is what we have for Earth. You get average temperature of 288. You get, there's a little bit of asymmetry because we've represented land just through the changes in albedo. You can see that at the bottom that the changes in albedo reflect where there's more land in the northern hemisphere versus the southern hemisphere. And so our control case looks pretty good. So moving on to TIE, the main event here. If we look at the benchmark case 1 in green, the lower curve on the bottom, we're really cold, and there's no hotspot. This is an EBM. It's one dimension in latitude. There's no transport from day to night side, so you essentially get a frozen snowball. If we go to benchmark 2, where I add a bar of CO2, well, we're quite warm. We have a very strong greenhouse effect, and you notice the albedo in the bottom plot, the albedo drops. That's from Rayleigh scattering. So you have a strong 1 bar CO2 atmosphere, and so you've got a lot of scattering. If we go to the habitable cases, it's quite similar. Now, for the first habitable case, we've essentially just changed the land condition, the surface condition, to an aquaplanet instead of land. And so we're a little bit warmer, but still not above freezing at any point. And then for the habitable 2 case is essentially almost indistinguishable from the benchmark 2 case because, again, there's no hotspot and we've got 1 bar of CO2, and so you've just got a strong amount of Rayleigh scattering that's dominating your albedo. Now, I will add a caveat that I was not able to finish the lookup table actually for an M-dwarf star, for a 2600K BT settle profile. So this is the correct planetary parameters. It's at 900 watts per meter squared for the star, but it is a solar spectrum from the radiative convective model. So this will be included in a publication, and I'll redo this figure with the right stellar spectrum. And so it will change a little bit, but I mean the basic message is pretty clear: is EBMs are really not adequate for these eyeball planets because they're just 1 dimension in latitude. You don't have any sort of longitudinal heat transport at all. I showed hysteresis at the beginning, but around an M-dwarf star, a planet has reduced isalbedo feedback. You really don't get this climate bistability at all, so EBMs don't really help map out that parameter space very much, other than just where are you frozen, where are you warm, and a GCM does a better job at explaining that. EBMs really are better approximations for the mean climate state for rapidly rotating planets. That would be fine for M-dwarf stars and G-dwarf stars, but the synchronous rotation really poses a problem. You could do this hybrid 2D EBM where you have a day side and a night side. I think one of Vicky Meadows' students is developing that. That might be a useful way to do it. But I mean, EBMs, the point is that they're very computationally efficient. Even with the lookup table method, you can do long integrations over million-year plus time scales. And so that makes them an interesting tool. But in terms of an intercomparison like this, I think it's really clear that you need GCMs if you're going to really understand what these synchronous rotators are going to be like. So thank you very much.